Alright, so the valence shell electron pair repulsion model called VSEPR, VSEPR, we normally call it VSEPR even though it's not really spelled VSEPR. But anyways, this will give us an indication of why compounds and molecules are shaped the way they are because of the repulsion of electrons that are involved in the bonding. So far, and again, as far as these notes go, you can take as little or as many of these notes as you want. If you want to just listen and start to, decipher what's important, what you think is important to write down, that's great. These notes will be on Student Share for you to email to yourself or whatever if you want to do that later as well. But so far, we've used Lewis structures or Lewis dot diagrams to account for the formulas of covalent compounds. One problem with Lewis structures, however, is that they do not show the shapes of molecules. They simply show the number and types of bonds between the atoms. When we draw Lewis structures, it shows atoms in the same plane, but the arrangement of the atoms in reality is three-dimensional. So it's important to note that when we're talking about shapes of atoms, and even when we draw, if we draw a bond between two things, or three things, or four things, or whatever, we have to realize that these atoms arrange themselves in three-dimensional space. So it's not just like on the page, right? It's three-dimensional space. And so what we're going to learn about is the theory that helps us determine the three-dimensional shape of molecules. I will be moving rather quickly through the notes. Like I say, if you want to take more, we can go back. But we're going to learn about let's take a look at page 324 first and look at the Ch4 molecule. The Ch4, that's the methane molecule. And of course, when we look at CH and we have this 4 under here, we understand that to be one carbon atom with 4 hydrogen atoms. And how are they arranged? Well, the hydrogen atoms are all the same, right? So they have the same electronegativity. They have the same sort of bond with the carbon. So the carbon is in the center, we see here, and the hydrogens are spread out. Now, it's a little bit tough to see this three-dimensionally when it's on a two-dimensional surface like this, but you can kind of understand that the carbon is in the middle and then the hydrogens spread out so that they're all exactly the same distance away from each other. Okay, they don't all group in the bottom or on the side, but they're all spread out. And so this is called tetrahedral geometry. Tetra means 4, tetrahedral geometry of methane. So we're just going to pause. We're going to watch this little video here, little animation on the VSEPR theory. So there's your basic shape. Basic shape if we have three atoms, 2 bonded pairs. That's a linear shape. And again, we'll learn all about these shapes as we move on, but just so you can kind of see them ahead of time, we'll maybe watch this video again after we've learned a little bit more. Trigonal planar. It's the bent molecule. Now this right here is those are electrons. Those are unpaired electrons, and as we'll find out, this is the same number of atoms and similar bonds to that linear one. But why is it bent? Well, it's because of extra electrons here that aren't paired. And this is the shape of a water molecule. Okay. So again, there's 2 sets of unpaired electrons there, but yet they cause the exact same bent shape. So remember, the red blobs there are electrons; they're not actually atoms. And it's called a lone pair. You see down there that is a lone pair of electrons that are unbonded. So there's your tetrahedral. That would be the methane as we saw earlier. And you can kind of maybe see as it spins there that as you mentioned before, are they the same distance away from each other, the hydrogens, or the same distance from the carbons? Because the bonds are exactly the same, the nature of the carbon and the hydrogen in each bond is the same, they're all the same distance kind of away from each other and the carbon. The distance between each hydrogen and the carbon pair, they're not necessarily the same, but everything is spaced out geometrically. Good old seesaw. That's the spaceship. I mean, square planar. I think you guys get the picture. I'll just kind of skip ahead. There's lots of different shapes that we will study, and basically what you'll have to do is you just have to recognize them and name them, and just understand how those extra electrons that may be involved affect the shape. The end. So interesting that at the very beginning of this video, okay, look at the VSEPR theory. VSEPR. Okay. All right. So I made a mistake there. What? Okay. So you get the picture there. Hey. These are the pairs that we're going to be studying. So let's just take a look at them sort of one at a time here. Okay. So the first one we're going to study is the linear one. Yeah. You want to draw this? Draw this out. At least draw the shape. Now the number of electron dense areas. Okay, that would represent the bonds there. Okay, so there's two bonds. This is where the electrons are between the central atom and this atom out here. So these are where the electrons are. And it helps you kind of understand the shape. Okay, so the geometry is called linear. And of course it's a straight line like the very first one that we learned about. And there are no lone pairs. So once again, the lone pairs, they're talking about electrons that are unpaired, that don't have an atom to bond with. And if there are unpaired electrons, then they change the geometry, which we'll see in the next one here. So what I've done just with the graphs here, or with the charts, is copied the first line, and then I've copied the first line again, so that you can, if you get behind in the notes, that you can kind of just catch up at your own rates. So we'll look at the second geometry. So the first one is linear, pretty basic. Okay, 3 atoms, straight linear. The next one is called the trigonal planar. Okay, now this happens when there are 4 atoms involved in the bond, and the one atom here in the middle is different from the other 3. And trigonal, think of tri is 3, right? So there's sort of 3 aspects to this shape here. And planar, the other part of the term, planar, means that they're all in the same plane. So it's a 2-dimensional plane. If you think about, the screen up there, right? It's just 2-dimensional, or your paper is 2-dimensional. And so it's trigonal, tri, 3 bond characters there, and then planar. Now I'm noticing that some of you are in your textbook when you do that. Right? Page 326, you'll see page 326. If you just flip to the next page, you'll see a huge chart of all these, and you can just follow along there as well if you want. But, okay. And I guess I should mention here before I move on that if we have an unpaired, one lone pair of electrons, we're going to have a similar thing happening. It's going to be shaped the same way, except these lone pairs are not an atom. And so that's when you end up with a bent molecule. And as I mentioned, H2O is like this. So let me just get my pen out here. So if we're talking about water, right, there's the O, here's an H, and here's another H. So this is the way we draw the water molecule, right? If you guys have ever seen me draw it, or you've ever seen it drawn, it's always like this. If we take a look at, where the bonds are, there's a bond there and a bond here, right? It's always bent. Why is it bent? Because oxygen would have a pair of electrons that aren't bonded to anything, and they would be kind of stuck out there, and they're repelling these hydrogens. So they're forcing the hydrogens to kind of be repelled away, and so it causes a bent shape, and that's from a one lone pair. So if there are 1, 2, 3 atoms bonded to a central atom, then you have a trigonal planar shape. If you only have 2, and you have a lone pair of electrons here, right, then you have a bent shape. All right, so moving on, the third row here in this shape would be a tetrahedral. So we looked at Ch4, the methane molecule, and that would be an example right here, tetrahedral, where we have the C in the middle and 4 H's. Now, how do you draw this three-dimensional? Well, if you draw the C and the H, okay, and the H here, this is how you can draw a three-dimensional molecule. You can do hatched lines. Okay, so this is sort of the way that we learned how to do it in university. You don't have to do this, but one of these means that it's kind of coming out towards you. This means that it's going back away from you, sort of thing. So you kind of get the three-dimensional look. The solid sort of connection there between the C and the H is sort of meant to be in the direction towards you, and then this hatched line there is sort of in the direction behind you. So you might see me draw stuff like that, but that's sort of why I do that. Okay. Now, if we had a central atom and three other atoms and a lone pair, then we would get a trigonal pyramidal. So tri would mean 3 bond areas there between atoms, and the pyramid, of course, is in the shape of a pyramid, right? So you kind of get this. So you have the triangular shape there, and then this atom would be sort of the top of the pyramid. If there were 2 lone pairs, okay? If there were 2 lone pairs here, then you would have a bent molecule as well. And actually, I mentioned water was bent. It is bent, but it's actually this is the representation for water. I'm not sure actually what I said. Yeah, I just drew 1 lone pair. Technically, there are actually two lone pairs of electrons. So, sorry about that, still early. But the reason why that is, and water is still bent, but this is the reason why, because oxygen has 8 electrons around it, right? So you have 2 electrons in this bond, right here. You have 2 electrons here, you have 2 electrons here, and then you have 2 that are unpaired here and 2 that are unpaired here. So 2, 4, 6, 8. Oxygen has 8 electrons around it. And, sorry, so here, so this would be water here. Oh, my apologies. So it's still bent, but it's because we've got 2 unpaired electrons there. All right. So our next, the next row, the next sort of geometry that we need to study here is if we have 1, 2, 3, 4, 5 electron dense areas. Now again, these could be bonds between atoms or lone pairs. If we have, these 5 dense electrons area, it's called trigonal. Okay, so remember, tri is 3, but it's bipyramidal. Trigonal bipyramidal is what it's called. So we've got it's a little tough to draw. So here's the drawing right here. Right, we have a central atom. You have these 3 right here. Maybe I'll zoom in for you there. That's quite a bit. Okay. Well, that's very good. Where were we now? Okay, right there. Okay. So trigonal bipyramidal. So you have the central atom, and then you'll see that this one, this bond, and this bond are all in the same plane. Okay. So that's sort of like a little bit of a T shape there, and then this one comes towards you. This one goes back into the board. Okay. So you have 3 on the same plane, and then you have one coming forward, one going back. And as I mentioned before with the molecular model kits, I want you to get to play around a little bit. Hopefully you'll be able to see, and it's a little tough to see here, but hopefully you'll be able to see that you would have a pyramid, oh, that's not right. You'll have a pyramid. Pyramid there, right? And basically you'd have a pyramid over there as well. Okay, sorry, it keeps popping back to where my cursor is. I'm going to bring this zoom a little bit. All right. Now, if we explore, the rest of those shapes, the sawhorse or the seesaw. This is also it's called a sawhorse, but I think in that video it's called a seesaw. So both of them are fine. I think I'll probably say the seesaw one. But here's where you have one lone pair, and so one of those bonds is not a bond anymore, and so you don't have an atom over here, and you have or sort of the 2 legs, and you have the a linear part right here. So that's the sawhorse or the seesaw. Called the seesaw. Two lone pairs. You have the T shape. Okay, so T shape here, and then if you have 3 lone pairs, if there's 3 lone pairs, then you have linear shape. Okay, because they're all spread out from each other, right? Remember, if they're unpaired electrons, they want to get as far away from each other as possible. So if there's 3, they will spread out in one plane, okay, at 120 degrees from each other. So they're evenly spread out, which pushes the other ones, into the other plane. Okay, so I want to go back to this this bipyramidal here. This is the way I'm going to draw it here. It's a bit easier. So you have, if you can see this, there's your one pyramid on the top, okay, with this central atom sort of on the bottom plane there, and then you have another one on the bottom. That's where they get the bipyramidal from. So. All right, so let's move on to the last one. I think this is the final one that we're going to look at here today. So to complete this chart, so you have everything here on the chart, all the way from linear down to octahedral. So there are 6 electron-dense areas here. Okay, so 1, 2, 3, 4, 5, and 6, and it's called octahedral. Now I know 6 is not octa. Okay, anybody know why they might call it octahedral? Okay, so octahedral. Again, it's gonna be a little tough to draw. I might zoom in here again. Okay, so there's one face there, right? There would be a second face. There would be a third face on this side, and then a fourth face on the other side. So that's 4 faces on the top, and then you have the same on the bottom. So there's 5. There would be 6 here, 7, and 8. Okay, so you basically have 2 square pyramids here, right? Right? So you have one, and then back side, and then this side, and the front side here. So a square pyramid has 4 sides, and you have 2 of them, and so you have 8 sides. Okay? See that? And the atom in the middle. So we have octahedral with 1 lone pair. Okay? It's a square pyramid, square pyramidal. So you take off one of these atoms, you just take one away, but you have the same geometry. You only have these atoms here, 4 atoms in a plane, and then you have this one extending straight out. And so you have a square pyramid there. With 2 lone pairs, remember the lone pairs are going to try and balance, like try and get as far away from each other as possible, because it's negative and negative repulsion, right? So the negatives, the electron pairs are going to be on either side here, which means you just have the 4, and that's going to be square planar. So it forms a square and is in the same plane. 3 lone pairs is the T shape, and 4 lone pairs back to linear again. Okay, so I'll just erase my markings and let you finish that up. So on page 328, you look at hybrid orbitals. Now we've talked a little bit about this earlier, but we never really went in depth with the hybrid orbitals. So you want to write this down for notes. This is just a summary of the notes from the textbook, and I've underlined some of the important things as well. So at times, overlapping orbitals morph into a special kind of orbital called a hybrid orbital. So again, this is from overlapping orbitals. In the case of methane, we'll probably talk about methane here, the s and p orbitals, and you know the s orbital is a spherical orbital, the p is a hourglass shape, but when they overlap, sometimes they morph into a special hybrid orbital. The name is just as it suggests, a combination of 2 or more orbitals. Okay, so it's kind of a mixture, it's a hybrid. This occurs often, but we'll focus on one type of hybrid orbital called the sp3 orbital. And again, on page 328, it gives you some good diagrams, sp3 orbitals. These orbitals form in the carbon, allowing 4 possible bonding domains. So the reason why carbon is sort of a can bond 4 different ways is because of this special overlap of orbitals. Okay, so how does this happen exactly? Carbon normally has 2 electrons in the 2s, right? And we know that from looking at the table. There would be 2s electrons, and there would be 2 p electrons. That's what it would normally have. One's a filled orbital, and 2 half-filled orbitals, and then 1 empty 3p orbital. But in reality, what happens is carbon rearranged itself, that the orbitals overlap, so that again they want to try and form the lowest possible energy setting basically on these orbitals, and so they form, out of these orbitals, they form 4 identical orbitals that are half filled. So instead of having 2 here, 1 here, and 1 here, they all combine so that they have 1 electron in each of these hybrid orbitals. So this is sort of what it looks like. The hybrid orbitals kind of have a large lobe and then a smaller lobe like that, and this is technically kind of what it looks like. All 4 of those hybrid orbitals. So instead of 1 completely filled orbital and 2 half-filled of the 3, there's 4 all half-filled orbitals. And this allows for maximum sharing of these electrons, right? These 2 electrons can actually split, and they can actually bond as well. So these 4 new orbitals are called the sp3 orbitals. The orbitals again spread out evenly in space, creating the tetrahedral geometry. So even though there's just kind of 1 electron in each of these special orbitals, those electrons repel each other, and they want to orient themselves so that they're as far away from each other as possible, which yields the tetrahedral geometry. Okay? So this little diagram here, you might want to make sure you copy this little diagram out. It's pretty important, how the orbitals sort of combine and what they look like. Okay, more complex hybridization accounts for double and triple bonds. Okay, so there are Single bonds, which is basically all we've been talking about here, single bonds. And I mean, we've been talking about compounds that have double bonds, but really the only types of bonds that we've been talking about, ionic bonds or covalent bonds, we've just been talking about single bonds. So I want to talk to you today a little bit about double bonds and maybe even triple bonds later. But single bonds, that's involving 2 electrons, are called sigma bonds. And of course the Greek letter sigma is used as the symbol for these single bonds. So a single bond is a sigma bond. That's probably pretty easy to remember. Double bonds, that's involving 4 electrons, are called pi bonds. And of course the symbol is the letter pi from the Greek. Sigma and pi bonds. Okay, sigma single, pi bonds double. And just to kind of show you why this happens, we're going to use Lewis dot structures, and we're going to use the octet rule, and we're going to talk about, how we know when this happens. So, okay, so just single bonds, double bonds, we'll skip that. Now, if we try to attempt to draw a Lewis dot structure, okay, for CH2O, you might draw something like this. Now, please note that this is not a correct Lewis dot structure. So you can hold off if you want, but this structure is not correct. Now, we might think, now O, this is good. O has 8 electrons around it. C is bonding with hydrogen here and hydrogen here. That all looks okay. But the only problem is what? Is that C is not happy because it does not have a full octet, a full outer shell of electrons surrounding it. Okay? So this is not a correct Lewis dot structure. So remember, C, it wants to have carbon wants to have a full outer shell, oxygen wants to have a full outer shell. Now hydrogen is giving up its electrons, so it can't really have 8. The maximum it can have is 2 because it's in the first energy level, right? So this is fine. Hydrogens are fine. But notice that carbon only has 6 electrons around it, so it is not happy. So how do we fix that? This is where the double bond comes in. Okay? So instead of single bonds around the carbon, a double bond is formed with oxygen. And this is how you draw CH2O diagram, where carbon has 2, 4, 6, 8 electrons around it. You see that? In the double bond, those 2 electrons are counted for carbon, and they're counted for oxygen as well. So here you can see that carbon is satisfied because it has 8 electrons around it. These 4 are included in that bond, so 4, 6, 8. Okay. And also for oxygen, and I'll just kind of maybe do this in red, oxygen has 2, 4, 6, 8 electrons around it as well. So that's how we know where a single bond might form and where a double bond might form. So this is a bond that involves 4 electrons, okay? And that bond's probably going to be stronger, right? It's probably going to pull these 2 a little closer together. It's going to affect the geometry in a way. Now here's some unpaired electrons, right? So again, those are still there. They're affecting the geometry a little bit, but we won't get into that. So carbon and oxygen are both satisfied because of their outer shell is filled. Now, the other thing that we're going to see a lot of here is called a structural diagram. And structural diagrams use kind of single lines for a bond. And this is, again, you're going to see this quite a bit here now in chemistry. This is, we're kind of getting into organic chemistry here a little bit as well. And so organic chemistry, there's a lot of structures that we'll be drawing. That's what you're going to see a lot of here. So, again, each line represents 2 electrons. And a double bond is simply 2 lines in between 2 atoms. So here's your pi bond, right here. And each of these are a sigma bond. notice the unpaired electrons don't get shown in a structural diagram. Okay? There's no unpaired electrons in a structural diagram. So page 325, we talk about bond angles. Now, the angles between bonds. Let's take that methane again, for example. Okay, so here we have the H's are all spread out evenly. So if we have 4, bonds, and they're all spread out evenly in three-dimensional space, what's the bond angle between them? And it's probably a little different than you might think. If we have something that's planar, let's say we have this right here, okay, trigonal planar, okay, trigonal planar. That's pretty easy to see that the angles between the bonds would be 120 degrees, right? Because it's 360 divided by 3. But when we're talking about three-dimensional space, we're talking about 4 different atoms bonded here, then the angle changes slightly. Now, you might think it's going to be pretty close to 120, but what do you think it would be, more or less, if you had to squeeze another bond in there? Now think about it three-dimensionally, right? If my hand was just flat like this, and now all of a sudden I needed to make room for something in one of these planes, they would kind of come towards each other, right? And the fingers would kind of start to come closer as they kind of went like this. So these angles between the fingers, okay, might be one way, but as you kind of have to make room for something else, that's kind of a weird thing, but you see how that works there? Yeah, how about this one? Okay, look at as they come closer to each other, you see how these bond angles right here actually would be, smaller? Okay? So, as we see on page 325, the bond angle here is, can you find it on the page? 109.5 degrees. It's a little bit smaller than 120 there. Okay? Now if we go back to this chart, it doesn't have it on the chart, but we could probably start to identify some bond angles here. So obviously, linear here, this would be 180, right? The bond angle. We already said this one here was 120. This is 109.5. Okay, so for the trigonal, bipyramidal, and the octahedral, what do you think the bond angles are going to be here? Well, this is all in the same plane, right? Yeah, that's 90. Okay. Now, the bond angle between this one and this one, though, what will that be? Well, I'm going to let you think about that here. These ones are all the same as well, but I guess it's if these are all in a plane like this, right? You have this one there's 3 in this plane, and this one there's 4 in this plane, right? So, anyways, between the ones in the same plane, it looks like it's going to be 90. But what about these over here? Or this one over here? There's only 3 in this plane, in the sideways plane. Okay. So, anyways, I'll let you think about that. There's questions about bond angles, so you can do some research in your textbook there as well. Okay. So on page 341, you have a chart of all the bond angles. So I'll let you look up the rest of the bond angles there and try and match those up. Okay, so that's number 3. And then when you're done, I want you to, because you might be done before the end of class, you have about 10 minutes, I want you to read up on what we're going to be doing next, and that's going to take a look at something called benzene on page 333, and then naming organic compounds is next. So do that question number 3, and then read about benzene on page 333 for tomorrow.